And we can start. Welcome back, folks. So for today's class, we're going to move into the next section, 4.4, on coordinate systems. And it's a pretty fun section because, as the doodles on the right kind of indicate, this is where we're finally, in an honest, full way, defining a real isomorphism between two vector spaces and actually using it to solve linear algebra problems. We've been teasing the idea of isomorphism all the way back in section 1.9, I believe, so quite some time. And so we've been thinking about all three of these concepts that makes up an isomorphism. The fact that T has to be linear, it has to be a one-to-one mapping and an onto mapping, just to kind of get prepared for this section 4.4. It's one of those sections which feels really kind of abstract. That's why we've been talking about what an isomorphism is in bits and pieces throughout the notes. But once you see how the problems come together and what the mechanics really look like when you use isomorphism, this will feel like another one of those sections that we probably could have done in chapter 1 if we could have somehow crammed it into that section, or chapter rather. So that's what we'll be doing today. The bigger announcement is we'll have our third exam next Tuesday. So for those folks in the in-person section, we'll just be back here Tuesday, November 11th, for the 75-minute exam. For the online section, check your message system in Canvas somewhere over here, or I believe this goes to your ISU email as well, for instructions on scheduling the exam. And if it's missing or anything like that, just reach out to me and I can resend those instructions. Well, we'll be working in section 4.4 today, but any questions whatsoever, folks, to start us out? Okay, well, maybe just a little bit more advice on studying for exam 3. The same comment that we've been saying pretty much all semester still applies. It applies to all the exams. Best way to start studying for this exam is just to get caught up on the homework sets. If you've already gotten completely caught up, good on you. I'll be grading section 4.2 as soon as possible and emailing you those results probably sometime on Friday. If you turn in a hard copy, I'll be scanning that. So watch your ISU email address and I'll send it back to you in that way. And after you get complete on the homework sets, then it would be a good time to start looking into these two versions of the sample exam problems. One version is the lecture notes, the other version is just additional problems with solutions at the very end. And we don't go too crazy on the exams. Pretty much if you've done the homework exercises, you've been participating in class, looking over the lecture notes before, exam questions are highly similar to what we've been doing all along. So you always have a pretty good idea what's really on the exam based off the homework sets and these two versions here. But with what we'll do now is jump back into section 4.4. And just kind of a brief recap on what we did in 4.3, we defined the idea of a basis. Then we found out how to find a basis for two particular kinds of sets. First, a basis is just a linearly independent spanning set. We found out to find a basis for the null space, you do the same kind of stuff you did over here. You find the null space first, but you go beyond the step of saying it's a span of set of vectors. The basis is those vectors without span in front of it. So make sure you take span off of it when you state the basis. A basis for the column space is even easier. You just row reduce a matrix to echelon form. The pivot columns of the original matrix A, that's the tricky part. The pivot columns of the original matrix A forms the basis. Now we're going to do a little bit more with bases in section 4.4. So here's how it goes. First, we, just for easy reference, have the definition of a basis right in front of us. A basis for a vector space V is an indexed listing or set of vectors, B1, B2, all the way through BP in the original vector space V. They'll form a basis for a subspace or for the vector space V itself, if, like we said, it's linearly independent and it spans. That takes us immediately to Theorem 7, and we kind of talked about Theorem 7 in the last section when we were discussing the role of independence and spanning. The unique representation theorem says, if you have a basis, so here's the basis here, we use the script B or cursive B to indicate it. If you have a basis for a vector space V or a subspace, then for every single vector X that you pick in that vector space, there exists a unique set of scalars, C1 through Cn, so that you can write X as this linear combination. Existence is through spanning. This is what allows us to find it. The spanning set spans the entire vector space V. So every vector in the vector space can be written as this linear combination. When we say unique, this is even better. Well, I mean, it's just as good, really. I can't really say better, but this is just as important because it tells us through independence, there's exactly one way to write down this linear combination. And because the linear combination is unique, the scalars C1, C2 through Cn are also unique. They're essentially the address to get to any vector whatsoever in the original vector space. Or another way to say it is, those are the coordinates for any vector in the vector space relative to whatever your basis is. One tricky concept about a basis is, you might have noticed the way we were writing down our answers in 4.3 was we said a basis for the null space or a basis for a column space. We never said the basis. Bases aren't unique. You can have multiple different bases for the same null space, for example. So if you change the basis, you'll also change the coordinates. So that's something to be very aware of. But if the basis stays fixed, those coordinates C1 through C2 through Cn are now unique. So this is kind of a fancy theorem. It has a name, the unique representation theorem. But once we state it, we directly apply it to creating a new definition. So really, we're just thinking about a basis all along in Theorem 7. We're working with a basis in this new definition, and this is where the new content truly begins, the coordinate vector of X. Any questions first, folks, with the prior definition of basis or the unique representation theorem? Okay, the color coding here in yellow is all about the new concept, the coordinates. So starting from scratch, suppose we have a basis B of vectors B1, B2 through Bn for that vector space V, and we pick some random vector X in that vector space. We'll say the coordinates of that vector X relative to this basis B is the scalars or weights C1 through Cn, such that X equals C1 times B1, C2 times Bn. So these are now the coordinates. And the way we write this coordinates down is in this particular way. So this right here, bracket X with a subscript B, is read as the coordinate vector of X relative to the basis B. So that's a mouthful. It says a lot in just a little bit of notation. Just to convey that, this whole statement right here is what this is read as. And all it is a list of vectors, C1 through Cn. These are ordinary scalars, and so those vectors go into Rn. That's where an isomorphism is going to come into play. The vector space V could have been anything, but if you're looking into the coordinates of a vector X, you can relate any vector X in that vector space V to some vector in Rn itself. That's if, one thing they don't say here, but this is only going to work if your basis is finite. So that's the one catch-all about this. It can break down with some bigger vector spaces. So let's just make sure we emphasize that. It's a finite basis. So this is the new concept. Essentially, we're just doing what we did in chapter 1. This is the linear combination from section 1.3, collecting those scalars and calling them the coordinate vector relative to a basis. And much what we're going to do in these notes is just practice with that concept. But here's where the transformation T hinted at the start of class on the Canvas page comes in. This transformation T, going from any vector space V whatsoever, maps to Rn. It's given in this way. Take a vector X from the domain vector space V, map to the coordinate vector. This is now an Rn, and we call this one the coordinate mapping relative or determined by the basis B. Key facts about this transformation T is linear. Doesn't take a long time to prove the linearity of this one. I'll refer you to the reading on this so we don't get too bogged down on derivations and proofs in this section. Another one that's a quick comment or concept is that t is 1-to-1. The reading again gives a nice proof of these facts, and t is onto. So this fits all three key ingredients for what we mean by an isomorphism. So the vector space V, if you can define this coordinate mapping, it says it's a finite vector space because there's a finite basis, or rather its dimensions finite. But the moment the coordinate mapping works from here to here, we have that T is an isomorphism. So we'll practice using that isomorphism T. But first, for the several examples we'll look into on these notes, this is more just about practicing the core definition for what we mean by a coordinate vector relative to a basis B. So that's a lot of concepts to start us out. Let's kind of take a moment to digest all of this. Any questions or comments so far? Okay, feel like a good cognitive break right there was a nice one to have in the middle. So let's start off in example one that just focuses on the core definition right here. We have three vectors, v1, v2, v3, defined in this way. We collect into the set B those three vectors, and it says this is a basis for R3. And you can take that for granted. You don't have to prove this. You don't have to take a determinant or do row reduction. You'll take for granted, trust me, this truly is a basis. What we want to do is find the vector x such that the coordinate vector of x is this one. X bracket xb 0, -3, 2 is the coordinates for this vector x. We want to know what is x. But really, we just kind of unwind what we were giving. If the coordinate vector relative to the basis b of x is c1 through cn, it just implies immediately you have this linear combination here. So these two concepts are completely linked up. So here's our coordinate vector relative to the basis. This implies x equals, take these three coordinates, go to the basis vectors, v1, v2, v3, which are analogous to the b1, b2 from this basis, and just write out x equals 0 times, let me match up the color coding, v1 minus 3 times v2, then plus 2 times v3. So here's the color coding to match up the definition with the particular example. And that makes this problem really fast. It's just a linear combination. We already know the scalars. We just have to crank it out, do the scalar multiplications, the vector additions. So in the next line, x is equal to 0 right away from the first term, scale v2 by -3. So this one will give us plus. I should write that in as a 0 vector, not just a 0, just for emphasis. So the next one is going to be 0, -6, -3. Scale v3 by 2, so this is now -10. 2 and 4. Then add these up, we get -10, -4, +1. And that's the whole problem. Kind of fun in a way. It feels like stuff we were doing all the way back in section 1.3, but just more machinery, more terminology. There's a basis now, and we're combining that with a linear combination. Focusing on the weights just means you're working with the coordinate vector specifically. So we're just connecting these two ideas, a linear combination with the coordinate vector, expanding out x, and this is what you get. Let's take a quick screen grab of this. There's kind of two problems relative to this definition. There's the fast problem, like we just did, but then the harder problem is when you know what x is right here, and you want to discover the coordinates relative to a basis. So we'll try that problem out next. That one's the longer problem, but it's really, again, not too bad. It's just a matter of connecting these two concepts together. Any questions at all? Finalizing example one. Okay, let's try it out again. Going in the reverse direction, here's a new basis. It's slightly different vectors. It almost looks the same, but there's a difference here on entry 3 for vector 1. Let's put the definition. Let's just park it down here for easy reference. And we're doing almost the same problem, but this time we know the vector x. We want to know what is the coordinate vector of that x relative to the basis b. So the basis here is v1, v2, v3 defined in this way. And here's one way to start this kind of problem. Start by writing down what the answer would be. The coordinate vector of x relative to the basis b is just a list of scalars. In the definition, you could call them C1, C2 through C3. Or if you prefer to do something more familiar, you could call this x1, x2, x3. Really, it's the same exact algebra either way. I'll go with the x1, x2, x3 approach. So we want to determine this. Once we find the values x1, x2, x3, the whole problem is over. So these are the unknowns, but we connect it back here into this vector equation. We are given an x vector. So we have, I'm going to write this equation backwards and put x on the right-hand side. We have x1 times v1. So x1 times v1 plus x2 times v2 plus x3 times v3 is equal to x. So if this is the coordinate vector, that means the scalars x1, x2, x3, or if you call them c1, c2, c3, are the weights on the linear combination that results in that vector x. And again, I switched the order of where x is, just because we typically would have written our vector equation in this kind of form. Our goal is to solve for x1, x2, x3. But if this is a vector equation, we could write this down as a system of equations. We could write it down as a matrix equation. Any notation is valid here. Or we could just write down the augmented matrix for the system, which is wise because that's how we're going to solve this. So take that whole vector equation. It has augmented matrix. Given this way, for columns 1, 2, and 3, we import the vectors v1, v2, v3 from the basis here. They're defined on the left. So it goes 1, 0, 3, 2, 1, 8, 1, negative 1, 2. Now we're going to augment with the vector x, 3, negative 5, 4. The variables are x1, x2, x3. So the moment we solve this, our work is done. We know something in particular about the coefficient matrix right here. Because this was a basis, this matrix up here is identical or row equivalent to the 3 by 3 identity matrix. And also because we're trying to fully solve for x1, x2, x3, we have to go for reduced row echelon form on this one. But really, it's just some typical row reduction operations like we've done before. We want to first eliminate this 3, so let me copy in rows 1 and 2. 1, 2, 1, 3. 0, 1, negative 5. Then multiply row 1 by negative 3, add to row 3, and we get 0, negative 6 plus 8, so a 2, negative 3 plus 2, so a 1, negative 9 plus 4, so a negative 5. So column 1 is now the first column of the identity matrix, and we just repeat here with this entry. So the 2, 2 entry, or row 2, column 2 entry, let's copy in that entire row 2 to start. 0, 1, negative 5. We need to eliminate entries above and below. We can copy in this whole column, though. It can't change due to the 0. So multiply row 2 by negative 2, add it to row 1, and we'll get 0. This will be positive 2 plus 1 for a 3, positive 10 plus 3 for a 13. And same operation, but adding it to row 3. Multiply by negative 2, add to row 3, and we get 0. This will be a 3 plus 1 for a 3 again. This will be a 10 minus 5 for a positive 5. I feel like I made a mistake. Let me try again. We're multiplying by negative 2, so that'd be 0. 2 plus 1 is 3. Ah, there's my mistake. That would have been a positive. Hang on. I think I made a mistake somewhere on this. This doesn't quite look right. Let me check my numbers. Anyone spot the error with this at the moment? Almost feel like I made an error getting to here.
Yeah, I had a negative 1.
That one right here? Or this one right here?
Yeah.
Gotcha. So for the negative 1 here, I'd be multiplying by negative 2, positive 2, minus 1 would have given me a 1. Yeah, that seems like more what I was expecting on this one. Thanks for spotting that. Good eye. So now with this looks a little bit more what I was expecting. I was expecting an answer that didn't involve fractions. So that's how I knew something was going awry on this one. And you know, that's a pretty good exam strategy. We do some pre-rigged numbers on the lecture notes, the homework problems, and I try to do the same in an exam setting. So if you ever notice the numbers are kind of blowing up, you're getting fractions with like 576 as a denominator, negative 724 as a numerator, something probably went wrong. So now this looks a little bit more like what we're expecting. We have columns 1 and 2 done, and we just need to resolve column 3 for the identity matrix. So another row reduction. Let's hide this below for just a moment. Row 3 goes 0, 0, 1, 5. This looks like the last step, so I'll put in the augmented reminder. Also, columns 1 and 2 can't change whatsoever, so let's just rewrite those entries. Take row 3, add it to row 2, and we get 0, 0. Negative 3 times row 3 added to row 1 is going to give us 0, negative 15 plus 13 for a negative 2. And at this stage, we're home free. Recall the variables were x1, x2, x3, or you could have called them C1, C2, C3 using the definition in its literal format. But either way you call these, we now have in row 1, the statement x1 is negative 2. Likewise, x2 is 0, and x3 is 5. But that satisfies the work we were trying to show. The moment we said the coordinate vector is x1, x2, x3, we solved or set up the vector equation. We've solved it, and now we can say, as an overall conclusion, the coordinate vector of x relative to the basis b is negative 2, 0, 5. And at that stage, the work is complete. So really, it's just a row reduction problem, but there's so much extra terminology. The fact that we have a basis that we're working with, we're maneuvering through a vector equation, row reducing it, and going back to a coordinate vector, the new piece of the terminology. This is what makes it all kind of tricky to start off a problem like this. But once you notice you're doing something very similar to what we could have done on weeks 1, 2, 3, and 4, really isn't too bad. It's just seeing how the terminology connects. Well, any questions at all, folks, finalizing this problem? Okay, you know, the check on this is so fast relative to the problem itself that we just solved, that's not a bad idea to just check it out really quickly. So if this is to work out, then the coordinate vector we just produced here is going to give us this linear combination we see down below, giving the vector x. So we put a border here to say the problem is over. This is just a check in the problem. Take negative 2 multiplied by v1, 103, plus the next scalar is 0, so I'll just say 0 vector as a placeholder, plus the next coordinate, 5, multiplying by the third basis vector, v3, 1, negative 1, 2. If we multiply this through, in row 1, we have negative 2 plus 5 for a 3. In row 2, we get 0 plus 0 minus 5. And in row 3, we get -6 plus 0 plus a 7. Or excuse me, plus a 10. That's a +4. Sorry, my arithmetic is not the best today, it seems. But that does give us the original vector x from the very start. And so that verifies this is the correct coordinate vector. Because we had a basis, we know something special about this coordinate vector. These are the only scalars in existence, -2, 0, 5, that can form a linear combination with the basis vectors v1, v2, v3, and result in the given vector x. There's no other way to do this linear combination. So that's coordinate mappings in a nutshell. What we're going to be looking into next, pretty shortly, is how does this work for vector spaces like P2, P3, and so on. But any questions at all, folks, getting through these first ones? Okay, well, let's move on to the next part of the notes. All of this has to do is with a basis. There's lots of different bases we can give for R3. We've already seen 2 of them just in these notes. Some bases are just more suitable for the method you're trying to run through. We're pretty interested in the standard basis for P2, for an example, but just for the sake of putting them both together, we'll also write down the standard basis for R3 on these notes as well. So it's basically a vocabulary question on example 3. These kinds of questions have a way to be like a concept questions on, say, this would be a final exam topic, not on exam 3. If you're ever told on a final exam setting as a quick concept question, write down the standard basis for R2, R3, R5, or so on, really this is all you'd have to write down. It does have a particular symbol. Instead of B for basis, we use E, cursive E if you like, but it could be just ordinary E. E is a good choice because the standard basis for R3 is listed as E1, E2, E3. It's a nice basis, but we'll see in chapter 5 the reason why we're interested in other kinds of bases, like the ones we were just studying in the last 2 examples. Sometimes the simplest basis is not actually the best basis for the particular problem you're studying. And if this is all you wrote down for example 3, if this was a final exam question, that'd be completely fine with me. But just for the sake of being specific, these are the vectors we mean. It's 1, 0, 0 for E1, 0, 1, 0 for E2, and 0, 0, 1 for E3. So that's the standard basis. And we can do the same thing for P2. But I don't think we've ever wrote down a standard basis for P2. We've done basis work in P2 before, however. We've showed, well, we didn't quite show we found a basis, but we did show something relevant. We showed that P1, P2 is linearly independent. It took a while. We had to equate coefficients. We showed that the vector equation has only the trivial solution. If we could show it spans as well, that would have been a basis. So we haven't quite written down a basis for P2 yet, but if you did have to write down a basis, here's a really good choice. Just like E1, E2, E3, in a lot of contexts, is kind of the simplest basis you can put down. For a space like P2, this is what it would look like. I'll write it as E because it's a standard basis, but it's a different one, so let's put prime on it, or any symbol you like, maybe a hat if you prefer. I'll go with the prime. It's not a derivative, just a different basis than the one we're looking at here. So this is going to be, well, they're polynomials, so I shouldn't write them as what is usually denoting a vector. Let's call them P1, P2, P3, or you could use Q. That's a good choice for a polynomial as well. And this is what the standard basis would look like for P2. First, you take the simplest constant function. Recall P2 is the vector space of all polynomials of degree at most 2. So it includes every constant. It includes the 0 function. It includes the constant function identically equal to 5. So our first basis vector should just be 1. If you rescale that vector there, you get every single constant. It also includes the linear functions, degree 1 polynomials. So P2 should just be the function t. Now, if you take linear combinations of, say, C1 times 1, C2 times t, you can write down any linear function whatsoever. And to get up to P2, the quadratic term, P3, you just put down t squared. So these are the standard order basis vectors for P2. If this was P5, then this would be polynomials of degree at most 5. And we would have had 6 vectors, 1, t squared, t cubed, t power 4, t power 5. So that's the connection there, this power 2 and this power 2 correspond to each other. And that's a particularly nice basis for us. We can write down any quadratic function just as a linear combination of these three functions rather. So this section is all about bases. Now that we have this basis, we can write down the coordinate vector of P relative to the standard basis of P2 in a really fast way, where this is the polynomial P. First, any questions with either one of those bases? Okay, example 4 is another one of those pretty fast problems. When you see this, it's kind of a vocabulary type of thing. It's something that we'll see written in a final exam problem potentially. We have to know that this entire statement means you're writing down this structure. Let me use a more official looking pen. This is what we mean by a coordinate vector. It's the coordinate vector for the polynomial P that was given. When it says relative to the standard basis of P2, we're talking about this one, and that becomes a subscript. So like we mentioned at the start of the notes, this is a really overloaded notation. It's talking about a lot of stuff in what's essentially just one symbol. And what this is a set of scalars, x1, x2, x3, or you could call this C1, C2, C3, that satisfy the following. C1, C2, C3 have to allow us to write this polynomial P of t as a linear combination of those three scalars. Well, that was a row reduction problem the last time we did this, but that's because we had a strange looking basis. This is a standard basis, and when you have a nice basis like this, it's not actually a row reduction problem. So here's the logic behind this. Since P of t can be re-expressed as 1 times, it's going to look strange, but it's 1 times 1, where that 1 that we wrote in green is a basis vector. The one in blue is just a first term that's listed here. That's not actually in blue, is it? Let me fix that. No, actually, let's leave it in black because we want it to be C1. So it can be written as 1 times 1 plus 3 times 3 coming from over here, and we'll multiply it by the second basis vector, t, plus 4 times t squared, because we can just immediately write P of t in this kind of way. We didn't do anything special. We're just indicating what the coordinates would be. But as soon as we did that, we're also looking at the basis vectors for the standard order basis of P2. So it's a super fast problem, unlike the last example that involved row reduction. But again, it's only because we listed the standard basis and it was asking for the standard basis again. So the whole solution to this is, therefore, coordinate vector of P relative to the standard basis E prime is 1, 3, 4. It's kind of a nice problem. We didn't have to fight with it too much. The work is complete immediately at that step. Any questions at all, folks, writing this one down? Okay, last problem we'll do in these notes is to show how do you do this if it didn't say the standard basis of P2. Maybe we're looking into other bases. And the next section, 4.5, we're going to be looking into very interesting bases. There's certain classes of polynomials called the Laguerre polynomials, the Legendre polynomials, and there's one other set that's just not coming to mind at the moment that have very, very wide applications to not just linear algebra, but other areas of mathematics, engineering, fields of physics such as quantum theory, AI computing, very vast different kinds of things. So different bases are of interest to us. And so we have to know, how do you do this if the basis is more complicated? Maybe they're Laguerre polynomials or something else we'll see in the next section. But if it's the standard basis, this is the whole setup. Any questions at all whatsoever, folks, getting the 1, 3, 4? Okay, so let's turn this over to a slightly harder looking problem. For the moment, let's get to just this part and discuss this problem, and then we'll look at the tools above example 5 that are going to help us out. So it says, show that this set of polynomials, there's 3 inside, forms a basis for P2. And they're strange looking polynomials, 1 plus t squared, t plus t squared, 1 plus 2t plus t squared. Somehow this is a basis. And think about what this is telling us to do. If we work just from very first principles, we have to show that set right there is linearly independent. And we've done something like that. That's where this comes in. We show just 2 polynomials here and here, P1, P2, were linearly independent. But that's a lot of algebra for just 2 polynomials. Algebra starts to explode as you add more and more polynomials to the list. This is 1/2 of finding a basis. We never showed what spanning looks like. If we do this directly, it gets pretty ugly as well. So this is one of those problems we probably wouldn't finish in our less than 40 minutes of time so far if we try to do it directly. There's other tools that we can use, and this is where the isomorphism, which we've been practically talking about all semester, finally comes into play. So here's the ideas. We need a transformation because working directly in P2 is not easy. There's a whole bunch of white noise. The fact that you're writing down polynomials at every single step, when all you truly care about is what's going on with the coefficients. The coefficients is the whole story. That's why we resolve this problem by just immediately going to a coefficient matrix as soon as possible. So we're going to do a transformation. It's going to go from the vector space V, in our case, V is P2, and W is going to be R3. So this is the example that we're going to work with our mapping. Linearity means these 2 properties are going to hold for us. And the definition of an isomorphism just means the transformation T we're about to define is going to be both 1-to-1 and linear. So isomorphisms play a huge role in algebra, mathematics in general. It tells us if we have an isomorphism, the 2 vector spaces, V and W, are exactly the same with respect to, well, vector addition, scalar multiplication, but it goes even deeper than that. Any concept that we can talk about in P2 carries over to R3 through the isomorphism, whether that's the concept of independence, spanning, basis. All of those concepts, including finding coordinate vectors, can all be done in a simple space. We translate over with the linear transformation. That is an isomorphism. So vector spaces that have that isomorphism are exactly the same. They have the same structure. And one concept that holds in a codomain or a domain will also hold in the codomain. So this is the mapping that we were discussing at the very top of the notes. If you have a basis B and a vector space V for a vector space V, the mapping that goes from that vector space V into Rn, defined in this way, producing the coordinate vector, is a 1-to-1 linear transformation from V onto Rn. It's in fact an isomorphism itself. So this problem right here is really tough in P2. But if we just use and abuse the fact that there's a ready-made isomorphism, the coordinate mapping, we used the coordinate mapping once already. There it is. We took coordinates. We went from the vector space P2 into R3. That's the actual coordinate mapping itself. This whole section is really about using that coordinate mapping. And this is how we're going to solve that this space or this set here is truly a basis. So let's start this out. So first, let's just make a quick statement that since, sorry, figuring out the right space to scroll to, since T mapping from P2 into R3 defined by T of P, we'll write it as a P instead because our domain is a polynomial space. T of P equals the coordinate vector of P relative to a basis. Well, that one's the one we're trying to show as a basis, so we need some other ready-made basis. And you know what a good one is? The standard basis of P2, so we'll use E. Since this is an isomorphism, we can solve the problem in R3. And we're pretty good at solving this problem in R3. That's where we get to use the invertible matrix theorem. We have a gigantic toolkit if we're in R3. We don't have much if we're in P2. That's why the work feels so much more painful. And just to define this, recall that E, we're writing it without the prime since there is only one standard basis we're writing down this time. E is the set 1 t squared. So if we're going to solve this whole problem in R3, here's what it looks like. Let A be defined by T at P1, T at P2, T at P3, where P1 is 1 plus T squared, P2 is T plus T squared, and P3 is 1 plus 2T plus T squared. So these three different vectors in the thing we're trying to show as a basis. So we're transferring the whole problem into R3 the moment we say this, because T goes from P2 into R3 itself. Another way to write this is, in other words, we're taking P1 relative to the standard basis of E, P2 relative to the standard basis of E, and P3 relative to that same standard basis E. And just to see this connect, here's P1, P2, P3, those three vectors here. And when we refer to the standard basis of P2, we're referring to these vectors, 1t, t squared. So this is a 3x3 matrix. So we can resolve this now in R3. We have A equals, we have to actually write down what these column vectors are to start working. First, this mapping for P1 relative to the basis E, if P1 is 1, 0t plus 1t squared, we just take 1, 0, and 1 to form the linear combination to make up 1 plus t squared. So this one goes 1, 0, 1. Likewise for this one, this is t plus t squared. So to form t plus t squared, P2, will go 0 plus 1t plus 1t squared. So those coefficients go 0, 1, 1. Does that make sense to folks at the moment on how we're grabbing those coefficients? Okay, it's a lot of machinery because to say exactly what we're doing and to justify it, you have to say what the mapping is. We're connecting it with the coordinate mapping. But really at its heart, all we're doing is going up to these polynomials, stripping off their coefficients. Coefficients for P3 is 1, 2, 1. So we're stripping those coefficients. 1, 2, 1. Those coefficients are the coordinates relative to the standard basis right here that forms P3. And that's our matrix A. And we can do a lot with that matrix A. We can say that the columns of this matrix A forms a basis for R3. This is what we mean by solving the problem in R3. If there's a pivot in every row, or if there's a pivot in every column, or we could just do something along the lines of, say, computing the null space. That seems like that'd be a lot of work, but the null space has just the zero vector. You also form a basis for R3. But maybe the simplest thing to do is just compute a determinant. If the determinant is like, say, 10, it's not 0, the columns of A form a basis for R3. But we got to the columns of A through the transformation T. So if columns of A are a basis for R3 over here, then P1, P2, P3 is also a basis for P2 at the same exact time. Every single concept in the domain space P2 carries over vice versa into a concept in the codomain space R3. Let's go for a quick determinant. I think that'd be the quickest way to resolve this one. Scroll down a little bit. We can say determinant A. It goes 1, 0, 1, 0, 1, 1, 1, 2, 1. And we could do a cofactor expansion across row 1 or down column 1. But let's do it in a faster way. Let's combine properties of determinants, and maybe eliminate this one right here to have a better expansion, a faster expansion. So we can go 1, 0, 1 to copy row 1, 0, 1, 2 for row 2. The row replacement operation doesn't change the value or the sign of the determinant whatsoever. So multiply row 1 by -1, add to row 3, and we get 0, 1, 0. It's not in a triangular form, but you know, this is a pretty fast expansion. We go down column 1, the 3 by 3 determinant turns into 1 times a single 2 by 2 determinant. Delete column 1, delete row 1, and take the determinant of 1, 1, 2, 0. It's a very fast determinant. Main diagonal is 0. Minus the off diagonal, -2. So this becomes -2, which is not 0. Now we just have to state our conclusions. We can say here, by the invertible matrix theorem, the columns of A forms a basis for R3. But that's not our ultimate conclusion. The last conclusion we want to state, and I'm almost out of space. Let me see if I can kind of compact this a little bit. The last conclusion we want to say is we have a basis for R3, and we got to R3 through an isomorphism. The original set B right here is now a basis for P2. So here's our big conclusion. Therefore, B, consisting of those original polynomials, P1, P2, P3, defined at above at right after part A, is a basis for P2 since T is an, Control Z's getting a little random there. Since T is an isomorphism. So that's a really slick way to show you have a basis for a more complicated looking vector space. It's a function space, a polynomial one. But you know, we've kind of hinted at before that when you write down the vector operations of scalar multiplication, vector addition, and Pn, P2 as well, it looks an awful lot like Rn plus 1 or R3 in this problem. We kind of had a feeling that these were isomorphic vector spaces. We just didn't necessarily write down in a complete way what the isomorphism was. Well, just not in these terms. We said it slightly differently by saying, grab the coefficients. That's exactly what we did here with the coordinate mapping. We just had to specify the basis to be sure, to be exact. This whole idea is a profound one in mathematics because, again, doing this directly, working in P2, this was half the problem in dependence. we got both independence and spanning in one shot the moment we just translated it over into an R3 problem. Well, any last questions at all, folks? Finishing this one. Okay. The sad thing about these isomorphisms, however, is there's one thing that kind of goes wrong. We mentioned that the coordinate mapping depends on a basis, and that basis has to be finite. So the one place that this is going to go completely wrong is if you try to do something like this. T going from V to something like CAB is undefined. The trouble here is when we try to do this kind of coordinate mapping, CAB does not have a finite basis. So the vector space CAB, the space of all continuous functions on a closed set from A to B, some of the nicest looking functions you could ask for, they're continuous for at least, it has some major problems. There's no nice coordinate mapping. You have to work differently to try to study that kind of space. But if you have a finite basis, if you're looking at a subspace of CAB, then the coordinate mapping does work out. We'll try out a couple more problems just for the sake of extra practice, dealing with coordinate mappings as well, and looking into the isomorphism one more time. Here's the next problem we're going to take a look into. We need to recall what the original basis was, so let me copy this down as a quick screenshot. So for the next part B, it says the coordinate vector of a new polynomial Q relative to the basis B, we're referring to this one down below, goes 1, -2, 0, determine Q of T. And it's good to look at the next problem at the same time to determine what are we doing in each one of them. For part C, we're going to grab a new polynomial. P of T is 1 - T squared. And we want to find the coordinate vector P relative to the basis B. So these are kind of backwards problems. They're much like example 1. This is similar to example 1. And this one is similar to example 2. One of them is a lot faster than the other, but the tricky thing about both of them is just determining what exactly you're doing in either version. Here's the logic on this one. What makes this one a faster problem, the thing that we have to recognize about it is this gives us the coordinates relative immediately to that basis B down below. So this is a problem where it's just crank it out to do the algebra, just like in example 1. Whenever you're trying to find the coordinate vector, this is the one that involves row reduction, like example 2. So to solve this part B right here, you just write out that if you have this coordinate vector, this immediately implies that the polynomial Q of T is defined to be 1 times P1 minus 2 times P2 plus 0 times P3. And that's the whole entire story on this one. They gave us the coordinates. Here's P1, P2, P3. We know those are the right polynomials because it said which basis we're getting coordinates relative to. So then on the next line, Q of T is 1 times P1, so that's just 1 times 1 plus T squared by substitution. Minus 2 times P2, but that one is just T plus T squared by substitution as well. Let me match that up. And then plus 0. So a really fast problem. Q of T is then equal to 1 plus T squared minus 2T minus 2T squared. So the polynomial Q of T is, let's see, 1 minus 2T minus T squared. And that's the fast version. Version C down below is a little bit harder, but just like on part A, there's a fast way to do this, and then an excruciatingly hard way to do it, just by first principles. Any questions at all, folks, running through part B? Okay, well, let's try it out one more time then. Part C is different now. We know the polynomial. On this one, the polynomial was given. Excuse me, the coordinate vector was given. But this time, if we have the polynomial, but we're trying to solve for the coordinate vector, the work looks a lot different. And think about how you might solve this if you're doing it from scratch. You'd be doing the same exact steps as this one. You have to write down an x1, x2, x3 times a p1, p2, p3, start solving for what this would be. The given polynomial would go onto the right-hand side. And this could take a good amount of work to start solving this down. But if we use the coordinate mapping again, the isomorphism, we can solve this entire problem in R3 and then just transfer back the coordinate vector. So that's how we're going to solve this one. Let's say first, if it says find the coordinate vector of P relative to the basis B, this means we need to solve for coordinate vector of P relative to the basis B will be set equal to sum x1, x2, x3. The moment we have those scalars, our work is essentially done. But again, doing this directly is hard, messy algebra, so we'll use T, the same transformation defined above, the coordinate mapping, to solve this. In R3. Here's what the algebra would then look like. We'll take x1 times t at p1 plus x2 times t at p2 plus x3 times t at p3 is going to be equal to, we'll put down here t at p. So this p right here is the original polynomial we're trying to work with. We have p1, p2, p3 coming from this basis, and the coordinate transformation is just going to give us the coordinates of this basis elements relative to a new basis, e, which is 1 t squared. So it's just like example 2, except all we're doing this time is peeling off all the coordinates on every single one of these and solving it in R3. Let's take a quick screenshot just to compare the methods, because it feels a lot more abstract when you're in a polynomial space and throwing a linear transformation on top of the whole problem. So just for a look at the parallelism on this, let's look at example 2 one more time. I think my color coding went backwards, unfortunately. Sorry about that last issue on the translation there with color coding. So imagine my color coding is flipped. Notice we're doing the same sort of thing though. Focus on the structure, and the yellow color coding looks correct. In place of T of P1, we have V1. T of P2, we have V2. T of P3, we have V3. And instead of X, we have in place T of P. So we're going to do the same sort of thing as before, but with the insistence of we'd rather solve this in R3. That's the fastest way to do this. So this could rewrite as x1 times the coordinates of P1 relative to the basis E plus x2 coordinates of P2 relative to basis E, the standard basis, written over here in the corner, plus x3, multiplying the coordinate vector of P3 relative to the standard basis E is equal to the coordinates of the vector P That's the original polynomial on the top. We want coordinates relative to this given basis at the very bottom. But we're pulling coordinates of the original polynomial relative to the standard basis E. So all I've done is output what the transformation T does. It gives us these coordinates. Next, let's fill out the vector equation by actually stating every one of those coordinates. We're back to that big mantra of linear algebra that we discussed on day one of week one of the whole semester. It seems like the more linear algebra you do in this course, the more it feels like there's a big theme of pulling coefficients. If P1 is 1 plus t squared, the coefficients of this goes 1, 0, 1. And it's in that specific order because those coefficients match up with this standard. Remember, it's an ordered basis from lower degree to higher degree. If you take 1, 0, 1 and scalar multiply, add them together, you get 1 plus t squared. So that's the first column vector, then go plus x2. P2, the coefficients go 0, 1, 1. Then plus x3. P3 coefficients go 1, 2, 1. Is set equal to coordinates of P relative to the basis E over here. Here's P, and those coefficients or coordinates would be 1, 0, negative 1. So that's the translation layer going from P2. Now we're fully working in R3, and you can solve this in your favorite kind of way. This time we need row reduced echelon form, just like in the example 2 that we solved. But it's really pretty quick once we write this down. Let me hide the basis for the moment. The augmented matrix would be this one, 1, 0, 1, 0, 1, 1, 1, 2, 1, augmented with 1, 0, negative 1. And the really cool thing about this whole process is, notice what you're solving for. This is the augmented matrix for the vector equation above. So column 1 is x1, column 2 is x2, column 3 is relative to x3. Get this into row reduced echelon form, and you have a value for x1, x2, x3. It carries up all the way to the very top. In other words, the moment you solve this whole problem in R3, you've also solved it in the domain space P2 automatically. Just like with this problem, the moment we found a basis for R3, it was a basis for P2 guaranteed. And now that we know it's a basis, we're going to find its coordinates of P relative to that basis. So it's now just an ordinary row reduction problem. We'll eliminate that 1 down below. So let's copy in rows 1 and 2. Row 2 is 0, 1, 2, 0. Multiply row 1 by negative 1. Adding below will give us 0, 1, 0. We're multiplying by negative 1, so a negative 2. A little bit faster than example 2's row reduction, it seems. Let's copy in both rows 1 and 2. 1, 0, 1, 1. 0, 1, 2, 0. Multiply row 2 by negative 1. Add it to row 2, and we get 0, 0, negative 2, negative 2. We're just about there. The coefficient matrix part will become row equivalent to the 3 by 3 identity matrix because we know that this is a basis already. Let's multiply that by positive 2 just to save an operation. Well, I don't know if that's a saving much. I'm going to take an extra step and just divide by negative 2 here into row 3. We get 0, 0, 1, 1. And just so that I'm not doing a bunch of row operations at one step, let me copy in the rest. Okay, so 0, 0, 1, 1. This looks like the final step. Because of those two zeros, we could just copy in columns 1 and 2 exactly as they come in, exactly as they were in the last step. Now here's where the row operation starts. Multiply row 3 by negative 2, adding it to row 2, gives us 0, negative 2. Multiply row 3 by negative 1, adding it to row 1, gives us 0, 0. But then this immediately tells us row 1 is the statement that x1 is 0. So we have our first coordinate. Row 2 is a statement that x2 is -2 for the second coordinate. And row 3 is just saying x3 equals 1, and we have our last coordinate. So now we go back to the top. We wrote down what we wanted in the very first place. Here it is. We just have to fill this out. We can say, for a big overall conclusion, therefore, the coordinate vector of P relative to what we proved as a basis in part A is equal to 0, -2, +1. And that's the long process, finding the actual coordinate vector itself. Verifying you have a coordinate vector is really quick. You just multiply things out according to these coordinates. So one thing you might want to do after you solve something like this, if you had a little bit more time in an exam setting, is just double check this really quick. P of t is supposed to be that thing right there. This is our official answer. But as a check, let's multiply this through and see if it really came out right, because this is some strange looking algebra, really. Take 0 times P1 at t minus 2 times P2 of t. Let me emphasize this is just the check part. And then 1 plus 1 times P3 of t. What we get is -2 scaling that polynomial. So -2t minus 2t squared. 1 scaling P3 is just +1 plus 2t plus t squared. Add up these like terms. Constant term is 1. -2t plus 2t vanish. -2t squared plus t squared is -t squared. And that is the original P of t. That comma t just kind of carried on. That was too big of a screenshot, it looks like. So we have the original P of t. Or did I type that in? I'm not sure what I did there. Yeah, that was just a misgrab on the screenshot. So ignore the comma t part. But this came out as P of t. That tells us we have the right coordinates. And that's really the whole strategy for this section dealing with polynomials. The polynomial arithmetic is sometimes so involved, like this section is hinting at, that what we want to take advantage of is really fast operations in R3. Whether it's the invertible matrix theorem or the fact that you can solve a system of equations really fast just by ordinary row reduction and getting the coordinate vectors that we were looking for in the first place. Well, that's the conclusion to this section, folks. Should put down the next section notes. We have a few more minutes and I've kind of added content at this point. But any last questions at all then before we call it a day? Okay, we'll revisit these ideas when we come back to section 4.5. Our main goal is to define what we mean by dimension finally. And then we're going to look into more bases like these. Certain classes of polynomials, like we mentioned, the Legendre polynomials, the Hermite polynomials, that was the missing one I forgot about, and the Laguerre polynomials. But have a great evening, folks. We'll end the class just a little bit earlier today, since we kind of just ran out of stuff to talk about. If you have any questions while you're studying for the upcoming exam 2 next Tuesday, don't hesitate to ask. I'll be available tomorrow. I'll be available across the weekend as well. But take care. Thanks. I'll get that scanned over and sent to you once I grade it. Okay. Yep, have a good one.